All right, let's suppose we have a first-order differential equation in normal form. So remember, normal form means that the highest order derivative is isolated. And for first order, that would just be the first derivative. So we like to call everything on the right just f of xy. And remember, in this case, y itself is a function of x. So we're just using f here as that placeholder for all the stuff that's on the right when you isolate dy dx. Now, even without solving this differential equation, we can make very good guesses about the graphs of its solutions. This is because we know something about its derivative. So if you pick an xy coordinate pair, and there happens to be a solution through that xy, then we can determine the derivative of the solution at that xy. So let's look at an example. Let's say we have this differential equation written in normal form. So let's say we didn't want to necessarily solve this differential equation. We don't even know how right now. But we did want to make some good guesses about its overall behavior in terms of what the shape of the graph of the solutions might look like. What we could do is we could say that if a solution passes through, say, and you just pick an x and a y value, say 3, 5, then its derivative at the point 3, 5 is dy dx, which is 2 times 3 over 5, and that would be 6 over 5. So if we were sketching the solution that goes through 3, 5, while we don't actually know the curve of the solution, we do know that right there, it has a slope of 6 over 5, which is just a little bit steeper than a slope of 1. All right, let's try another point. How about the point 3, 3? Well, its derivative at 3, 3 would be 2 times the x coordinate divided by the y coordinate, which would be 6 over 3, that's 2. So if a solution goes through the point 3, 3, we know from our differential equation that it has to go through that point with exactly a slope of 2. So it would be, that's a little bit steeper than the other one, something like that. Okay, let's try 3, 7. So 2 times the x coordinate, 3 divided by 7. That's 6 over 7. That's a little bit less than 1. All right, well, one could imagine filling the entire xy plane with these little slopes everywhere. In fact, if we were to do that, this would be called a slope field. They're also called direction fields, and in fact, our textbook calls them direction fields. So, understandably, it's fairly painstaking to generate a direction field. Imagine if we had to do this for from negative 10 to positive 10 on both the x and the y axes, then we'd be doing 100 of these calculations. So we typically leave this work for computers to do. As the convenience of Desmos knows no bound, it includes a slope field generator or direction field generator, as you can see here. Now Desmos does call what we call f of xy, it calls g of xy, so, well, I think we'll be all right. So here I've loaded up our 2x over y differential equation, and there's the slope field for it. So just imagine doing that by hand in the pre-Desmos universe. All right, and I've pasted that direction field into our notes here. And comparing it with the 3 points that we found manually, it seems like we were on our way to generating the whole thing. And once you have this direction field generated, you can easily actually graph proposed solutions. So for instance, let's sketch the solution passing through 0, 5. So on our direction field, let's find the point 0, 5. There it is. Now we can see that right at 0, 5, the slope is 0. And you can calculate that by plugging 0 and 5 into 2x over y and getting 0, of course. Now what that tells us is that right here, the solution through 0, 5 is flat. But let's track the behavior as we move to the right. So the curve will move to the right, but notice that as it moves to the right, we now encounter what appear to be very shallow positive slopes. So we can probably expect our curve to start to move up like that. And the basic idea here is that as your curve moves, you look at the slopes in the direction field around the area you're working to get an idea of how your curve should continue to progress. The slope would just follow these guys, and you can see that it's just taking on these approximate slopes here, and we get something like that. And on the other side, same thing. It comes out fairly horizontally. It hits some very gentle slopes here, and it sort of seems to be between these guys going up roughly in that direction. And that would be our answer. All right, let's do one more. Let's sketch the solution passing through, say, 5, 2. So 5, 2 is right here. All right, so first thing it encounters is this row of red slopes that are about that steep. So we can try to mimic the steepness there. Then we encounter this row of purple slopes and get a sense of the steepness. And then we encounter these orange slopes and get a sense of their steepness. And so far this seems like a pretty straight line, but now it's starting to curve a little bit because these black slopes are noticeably shallower, but not that much. And once we get to these blue guys, it's going to be roughly parallel to those once we get to these green ones. So this one's very subtle. On the other side, it's getting steeper. And there we are. You might recognize these shapes from pre-calculus when you studied conic sections. These are hyperbolas. In particular, the family of solutions is 1/2 y squared minus x squared equals a constant. And if we turn that on, you can see the hyperbolas. There was our solution through 0, 5. And there was our solution approximately through the point 5, 2. So just by generating a slope field and making some good guesses about the curves, we were able to get very accurate sketches of these solutions, and we did nothing analytical to solve this differential equation at all. Okay, as annoying as it is to produce a direction field for any old first-order differential equation, an autonomous first-order differential equation is significantly easier to work with. In fact, with very little work, you can make a high prediction about the shape of the curve and the overall behavior of the solutions. And this is good news because if you just look back through the first few lectures, a large percentage, if not most, of the differential equations that we saw happen to be autonomous. Now, we didn't officially define it, so we should do that right now. An autonomous differential equation is a differential equation where the independent variable does not explicitly occur. So the one we saw a moment ago, which was this guy, is not autonomous because of the x, which is the independent variable. However, if we just got rid of the x and dealt with this different differential equation, that one is autonomous because it just involves the dependent variable and the derivative. So why do we love these and why does it make our lives great? Well, the direction fields, they don't vary horizontally because the x coordinate doesn't factor in. Okay, we're back to the Desmos direction field generator, and you can see that the differential equation that we left off with is, of course, not autonomous, but if we took out the x, then notice that we now have an autonomous differential equation, and the direction field is horizontally consistent. Now, this is particularly convenient because Desmos shows a different color for each row, and you can see, for instance, that all of these guys have exactly the same slope, and all of these guys have exactly the same slope, and all of these guys have exactly the same slope. So that's what I mean by horizontally consistent. Let's put in some of our favorite differential equations that we've worked with. So the population model that we worked with last time was dp dt equals k times p. Now here we'll have to use k times y. We'll add a slider for k. And of course it's autonomous, and you can see its direction field is horizontally consistent. Let's look at one we haven't seen yet. How about sine of y? Well, that looks pretty cool. Again, horizontally consistent. But the moment we put another variable in there, like sine of yx, well, now it's just early 1980s wallpaper. Let's take a look at that market penetration model. So remember, this was a differential equation that tracked the spread of an idea or a disease or a new innovation through a community of n people. So n equals 1 isn't very interesting. So let's go to, say, n equals 6. And let's notice a few things. First of all, when y is equal to 0, all the slopes are perfectly flat, meaning if 0 people know this rumor at the start and it's a closed community, then no one will ever learn it. It's just always going to be 0. And the same with 6. If everyone in this community knew the rumor, then it's just going to stay that way. It'll be 6 today, it'll be 6 tomorrow, it'll be 6 the next day, and so on. Now, this is a common behavior in autonomous first-order differential equations. So much so that we have a name for these points, 0 and 6 in this case. They're called critical points. And if you think about it, this comports with your idea of critical points from freshman calculus, where critical point was simply where the derivative was equal to 0. And that's true here as well. All right, so a critical number is essentially where dy dx is equal to 0. And for an autonomous differential equation, which is written here in normal form, of course we don't have fxy, we just have f of y, because the x doesn't exist in an autonomous differential equation. So if the derivative is equal to 0, then f of y is equal to 0. And this allows us to locate the critical numbers of an autonomous differential equation very easily. And as you saw in the direction fields we just looked at, the critical numbers tell a big part of the story about the behavior of the solutions. In fact, critical numbers are also called stationary points or equilibrium points because of that behavior. And let's finally note, before going into an example, that if C is a critical point, then y equals C is a solution of the differential equation. Popping back over to Desmos to take a look at our direction field, in this case we saw that 0 and 6 were the critical points, and that means that the horizontal line y equals 6 and y equals 0 are both solutions to this differential equation. And indeed, they conform trivially to the slopes that are in the direction field here. All right, let's consider the differential equation. dy dx equals y squared minus y to the 4th power. Now you can see this is autonomous because there's no independent variable x, in this case, anywhere in this differential equation. So what we're going to do is pretty much analyze the overall behavior of the solutions here and even sketch some solution curves with very little work. So the first thing we should do is find its critical points. Okay, well, this right-hand side in normal form, we're going to call that f of y. So to find the critical points, we're just going to solve f of y equals 0. In other words, y squared minus y to the 4th equals 0. Y squared comes out, leaving us with 1 minus y squared, and oh, that factors even more. So we can see critical points y equals 0, y equals 1, y equals negative 1. All right, and let's just note as an aside that these are all three distinct solutions to this differential equation. I mean, let's quickly just verify that y equals 1 works. So on the right side, 1 squared minus 1 to the 4th is 0. And on the left side, the derivative of 1 is 0. So, yay, it works. Okay, to get into our analysis of this a little, what we're going to do is create what's called a phase portrait. So what's a phase portrait? Well, it's basically a direction field for autonomous equations without needing all the extra junk that a direction field has, because an autonomous equation has so much regularity in it. So it's really just a vertical line. And on the vertical line, you place the critical points that you found. Now, between each critical point, we're going to test the differential equation for a y value in that interval. For instance, when y is greater than 1, we can see that dy dx would be negative because, for instance, just pick something greater than 1 like 2. 2 squared is 4, minus 2 to the 4th, which is 16. 4 minus 16 is negative. When y is between 0 and 1, again, evaluate your dy dx. Let's choose something like 1/2. 1/2 squared is 1/4. Minus 1/16. Well, that'll be positive. Now let's choose something between -1 and 0, like -1/2. Well, again, we're still going to get positive 1/4 minus positive 1/16, so that'll be positive. And finally, let's choose a y value less than -1, like -2. And of course, we get positive 4 minus positive 16, so that'll be a negative for our derivative. Okay, so we indicate this on our phase portrait by drawing either an upward or downward arrows. So for this particular region, since the derivative is negative, we'll draw a downward arrow. Then over here, positive derivative, and here, positive derivative, and here, negative derivative. Okay, so this is our phase portrait. And we get a lot of information about the behavior of the solutions just from the phase portrait. Now, before we interpret this and actually draw some sketches, let's go over how we can classify the critical points based on whether or not the arrows are pointing in or away from them. This critical point right here is called asymptotically stable. Notice that both sides are pointing inward toward that point. This means if you have an initial value problem and the y value of that initial value problem is very close to 1, whether it's above or below it, the solution is basically going to curve in toward 1. This is also called an attractor.
Linear equations? Strange attractors.
Okay, let's take a look at this guy right here. Notice at -1, whether you're above or below it, the arrows are pointing away from -1. So this critical point would be considered unstable, and it's also called a repeller for obvious reasons. And finally, this point here, where y values below it are climbing into it, but y values above it are moving away from it, that's called semi-stable. All right, well, how do we graph solutions to the differential equation based on the phase portrait? Well, first you place the critical points in as horizontal asymptotes. So there's 1. There'll be a horizontal asymptote right here at 0. And there's 1 at -1. All right. Notice that 1 is an attractor, which means as we move to the right, the curves are going to be approaching that line asymptotically. So if we started above, we're going to come down toward the 1. And if we started below, we're going to come up toward the 1. Okay. And 0 is semi-stable. In fact, above it, we're moving away from the 0. There, above it. However, below it, we're moving toward the 0. And -1 is a repeller. It's unstable, which means solutions move away from it. And we don't really know where their horizontal position are. I'm drawing many, many possible solutions to these differential equations. We haven't solved this differential equation at all, but yet we know what its solutions are going to look like. If you focused on a particular initial value, say right here, then the solution through there is almost certainly going to look something like this. And remember, the asymptotes themselves are actually solutions. Y = 1 is a solution, y = 0 is a solution, and y = -1 is a solution.